study in a moment to at least try to numerically and visually try to understand the question, which prior and why. So we have a definition so far on conjugate priors. So it means if your prior distribution is the same distribution, lives in the same distributional family as your posterior distribution, the prior is set to be conjugate. So what that means is in a sequential analysis, as you're seeing data coming in, you're just updating the parameters underlying the distribution. You're not changing the functional formula. And so that's kind of nice. So just to illustrate that point, if I were trying to be really consistent, I might write something like this right here. Pi theta given x. So this is a distribution of theta given the data x. And I would say this is equal to likelihood times prior distribution. And I'm using the same pi here to denote it's the same sort of function over theta. Now, a lot of people aren't super consistent about that, but it's saying this is a distribution over theta, this is a distribution over theta. And I kind of like the way it's written here because it's telling me that here's what I believed beforehand, or at least how I modeled my beliefs, whether they're diffused, and I'm modeling ignorance through them. So like a flat prior or something like that. So some model of ignorance that you don't know anything, and then I'm going to update my beliefs with my data. And there's a functional tie between those same parameters and the data x that you've observed. And you're going to update your beliefs now, conditioning on x. So in terms of the language, a lot of people like to say this is what you believed a priori, and this is what you believe a posteriori. Now it could be that in a sequential analysis, and you're updating seeing the data, but this could also model ignorant beliefs. So you don't have to believe anything per se. So that's probably bad language that makes everybody think you're a super subjectivist, and what are you going to do about it all? Fun mind games, fun things to think about, but in practice, maybe not great. I should probably finish writing the denominator here, just so I can use that equal sign, pi theta, d theta. And I integrate over the whole universe of theta. So this is a definite integral, and it means that I'm integrating over the bounds on this integral. So for a normal distribution on mu, that would be negative infinity to infinity, and theta would represent mu. If theta was representing p in kind of a generic notation in the Bernoulli analysis, then I'd be integrating between 0 and 1 right here. So, but the concept is still the same. So we have to talk a little bit more about how do we pick this right here, but we're going to stick in the class of conjugate priors for a moment. Later on, we can mix it up and use things that maybe don't look conjugate or we don't think of that way, and there's other good reasons to pick certain priors. It turns out that within the class of conjugate priors, once I lock down some of these parameters here that underlie those distributions, I can have other properties that match other prior types. So it doesn't have to be subjective where I say this is what I actually believe these are. So I don't think I'd ever be able to go to a scientist and say, okay, well, we all agree your data is Bernoulli distributed. Thank you very much for showing me a vector of zeros and ones. It passes my test for independence if you bin everything up, so I don't see the ones clumped too much and the zeros clumped too much. What do you think the parameters are in your beta distribution for your prior? No scientist is ever going to be able to answer that. Well, I think you should pick clearly 0.01 and 0.2. So why would they pick those numbers? So we have to have good reasons for picking these right here. So other prior classes end up converging into members of these families right here. So this is saying that I'm going to pick a prior, and it's got two arguments in here. So this is a full family of prior distributions. So there's other types of priors out there. I'll mention a few of them. Jeffreys priors, reference priors, for instance. There are empirical Bayesian priors, and we'll go into that, and that's kind of a different thing. But it turns out in this one-dimensional analysis, where I'm just trying to infer what P is, there's a reference prior that tells me which alpha and beta to pick. There's a Jeffreys prior that tells me which alpha and beta to pick. And there's other analyses that tell me which alpha and beta to pick. Turns out the reference and the Jeffrey prior for this analysis are exactly the same. So that's very nice and reassuring. They're actually guaranteeing two different things, but I get the same prior. So sometimes you can have two things at once and sometimes you can't. So that's what a lot of this class is going to be about. So we'll first address this through our simulation study, and in a few weeks' time, I'll derive a particular prior for you. But the prior that I want to eventually talk about is 1/2, 1/2. Right here, beta half half. I'm going to tell you that it's a good prior. I'm going to show you some reasons why it's a good prior, and later on we'll derive that. But we already know, we're thinking, well, that's pretty good. Alpha and beta probably should be the same as each other to express ignorance on whether or not p is bigger than 0.5 or p is less than 0.5. And that's kind of meaningful to us because that's usually the break point that we're talking about when we say flip a coin. So we're thinking about 0.5 or at least close enough, somewhere around there. And the question about the size on these things, we're inclined to think those things should be small. So remember the resulting posterior that we get out of this analysis, pi p given x. This is going to be a beta distribution, alpha plus sum of the xi's, comma, n minus sum of the xi's plus beta. So this is the number of successes. So I'll say the number of heads, and this is the number of tails. And there was a question last time, and I'm going to answer it only very roughly. Right now, if we were trying to understand in this specific problem what the rate of influence, i.e. in that picture when I was simulating everything and I was seeing more data, we could see that the posterior distribution was pulling away from the prior distribution. And the question was, is how fast does that happen? And that's a good question. And if you like answers like that and you like thinking about it, that's kind of what objective Bayes is about in some sense. That's exactly what reference priors are measuring, is how fast your posterior pulls away from your prior. So that's a good question. So how much influence does the prior have? In this specific analysis, you can start to answer the question just because this is a linear function and we understand adding things up. So how much does this matter to this thing incrementing right here? And so you kind of have a sense of how fast the data is coming in, and the same thing for this one. This is accumulating zeros. How fast is that right here? So if I ended up saying something like 1/2 and 1/2, I might be thinking of the prior is accounting for a fictitious data point. And I'm getting some noise around that fictitious data point. So I don't want to be too certain, I'm putting a distribution on it. So I'm saying there's a fictitious data point here, and there's a fictitious data point here, but since I'm being fictitious about it, I can say this doesn't contribute as a full data point, this contributes as a half data point. And this is like a half failure. So in some sense, the prior distribution has as much weight as one data point. So sometimes you can look at the arguments in your posterior and just come up with a conceptualization of what that rate is. So I would say in this analysis, using a half and a half here, your analysis is very akin to throwing in a half success and a half failure into your analysis, if you could do that. And for a Bayesian, this is just some parameter, and I could throw that in. You might say, I don't feel very good about that. I want this to be 1 and a 1, so I can explain this to people. I'm talking to my mom. You know, what are you talking about a half success? It's a good question. You have to go through lots of advanced math classes to accept things like this. So, and go, okay, I guess that's okay. So you might say, I want this to be a 1 and a 1 right there, and my prior's acting like 2 data points. And it's like seeing a success and a failure. So at first, I'm thinking that I flipped the coin 2 times. That's how the prior's acting, and it landed heads and tails. Is that biased? If the coin was like a 0.9 or something like that, that prior is incredibly biased away from the truth. So A true point of having a probability of 0.99, I should be stacking weight around 0.99, but I don't know the truth. So how would I put weight there? So it's fair in some sense, or objective in some sense, to model your ignorance and say this number should be the same. Of course, changing the scale of whatever that number is going to affect the variance and how you're stacking mass everywhere. We'll do the same thing and look at the normal distribution, and later on I'll give you more mathematical things where you can write limits and see what happens.
By that same logic, why do we stop at 1/2? Like, I don't want to go down to 0.1.
Yeah, why not down to 0 all the way down? So this is called Haldane's prior. So, and we'll play around with it, and it turns out you might think, well, I don't really care how I pick these or how my prior is acting. I care about this and how fast it converges to the truth. And so I might be interested in that, and I want some optimal rate of convergence towards the truth. And so we're going to talk about why we even want to place any maths on this at all. This is, if I ended up putting a 0 and a 0 in here, it turns out there's no such thing as a beta 0, 0. It's an improper distribution, so if I integrate over it, it integrates off to infinity. Now for a Bayesian, they don't care. You know, a modern day Bayesian, probably 100 years ago, this would create some like mental explosion. What does that mean? How do I think about it? If I give you the engineering approach first and say we do it all the time, and the properties are good, usually you're inclined to go, okay, I can accept that. I can use an improper prior distribution because all I care about is this thing. And so there's lots of arguments, namely Jerry Brown over at the University of Pennsylvania back in the 70s wrote a really nice proof as to why this is optimal. And it's optimal in some sense. Turns out it's Jeffreys, it's transformation invariant. It's also the reference prior, so this is the prior distribution that has the posterior pulling away from it as fast as possible. So that's really a neat thing. You need to know the calculus of variations to actually do that. So I'm going to show you what that means at the end of class. So when you take an advanced class, they can say, go take a calculus of variations class first. So working through those things can be a PhD in itself. But I'll tell you what it all means, and then I'll tell you certain things are true. But I will say, in one-dimensional analyses, computing reference priors is as easy as computing Jeffreys priors. And there's a proof that says they're the same thing in 1D. And it took them decades to figure that out. So once we get more into that, I'll tell you more about that story. So I'm not going to do it all at once. Instead, we'll try to answer this a little bit computationally. We'll see what the beta half-half looks like. Later on, we will drive this explicitly. So we'll play around with it. You might be saying, hey, look, I want to play around with a uniform distribution. I can explain that to my mom really easily. So she'll get that. This beta half-half thing is going to weird her out. If she's thinking enough about this, she'll understand this. So if she can think about a beta, she can do that. So, I think I'm saying too much about it right now without actually doing things. So I'm going to tell you more about this, where that half and a half come from. I guess I could say this. If I were interested in a parameter like this, and homework 1 has you play around with this, transformation of variables, if I ended up looking at this parameter, the log odds, I'm going to say log p over 1 minus p. So this is the odds ratio, this is the log odds. Sometimes people like to look at this function and not actually p. So, and if you've ever played around with logistic regression, that's a function people like to play around with. It's smooth. It lives between, where does this thing live? The whole real number line. And so sometimes people like to map that to not deal with the boundaries. So they'll think about this thing because they can just model this parameter living between negative infinity and infinity and squeeze these things into regression frameworks. I will say, if you were thinking about this parameter, and you placed a uniform distribution on that, it would be very different from placing a uniform distribution on p itself. So those mean different things, and if you understand transformation of variables, you will understand that statement. When you transform uniform things in nonlinear fashions, you make them incredibly non-uniform. So modeling beliefs on uniform scale, you better think about that parameter very carefully if that's what you want to do. That's what a lot of this class is about. So again, which prior and why. I wish I could say if I could have one thing in the mathematical universe, it would be if I could transform uniform priors to anything and they stayed uniform. Of course, that doesn't make any sense. You'd have a fundamental breakdown in what number systems actually meant. So, can't happen. I wish I could also say, forget the prior, just do inference off of the likelihood function. And that's essentially what Fisher was suggesting to do so he could circumvent the prior. And in the normal analysis on mu, that's a perfectly okay thing to do. And so there's lots of ways to think about that. Would I do that also for P in a Bernoulli? I wouldn't. Let's look at the simulation study. Okay, I have some pictures. I'm going to show you these pictures in a little bit. If you're familiar with that picture and what it means, that's one of the reasons why I like a beta half-half. I'll walk you through that in a moment. Homework 2 is meant to ask you to draw that picture. So implement it, write some code. So let's just rerun our analysis. Let's pick some different numbers for our starting point. So just trying to remember what all this stuff means. So 0.4 is the true probability of flipping the coin. So every time I sequentially update my posterior, you can think about this as doing Bayes' theorem on the whole data set, but all I'm doing in the code is I'm just incrementing this number. So I flip a coin, if it lands heads, I add a 1 to that. If it's tails, I add a 1 to that. So, and that's all we're doing, so that's the sequential update. One more time, thank you very much, you're doing great. So 0.4 is the coin. Anybody have a number that they want? You don't like 0.4s? 1, exactly, thank you very much. I was wondering who was going to mess with me. So, we could do 1. So will it break my code? Colby is going to challenge me all the way through. I used to think the same thing, and I mess with them. So let's look at the boundary effect. What should the prior be?
10-1.
10-1. Okay, cool. So you said 1, not 0.1.
I said 0.1. No, I'm kidding.
Oh, okay. Oh, that's easy then. Oh,
I
wow.
wasn't trying to mess with it.
That's my prior.
That's it, I mean.
Right over there. That's a good one. Okay. Here we go. So I flipped it 50 times. I think that's a really good experiment. It kind of stresses everything. The beta distribution, beta 10-1, stacking a lot of mass over on the positive side. The posterior distribution is a superposition between the likelihood function and the prior, meaning that essentially I'm just multiplying every point that I'm computing, and that's exactly what my code does. It just multiplies those points. You can do it across a function if you have a real continuum. My computer doesn't know what that means, so I just put this on a grid and computed this at every point, and then I normalized everything for you. And that's really the answer to this right here. Expectation of theta given x. You need to normalize everything. So you multiply those numbers together, you need to divide them by the sum of all those numbers when you do all of that. That's part of Bayes' theorem. The likelihood's over here, we know what that looks like. The neat thing to notice is the likelihood is covering the truth very nicely. You know, not exactly in the center, but it's definitely stacking mass over there. The likelihood doesn't think P's over here, so the likelihood's doing a lot for us. Any other numbers? So pick smaller ones, see how it goes. I mean, we could crank this number up right here and flip it more times. Boom. See what this does more in the limit. You can see that the posterior distribution is getting spikier and spikier, and the likelihood has gotten very spiky. So this is a rather sticky prior in some sense. The good news is if you flip the coin a heck of a lot of times, if you have a lot of data, maybe it doesn't matter what the prior is. Now, this matters to me. I don't like saying this. I don't think the answer is around here. I think the answer is more to do with the likelihood. So again, if you can't defend what your priors are and they have rather strong beliefs like this, you're going to have a hard time convincing somebody that the truth is in here. Let's make this really sticky. This is acting like 101 data points, and my actual coin flip is just 100. So it's gonna probably not work very well. You can see what's going on. So let's finish the thing. So the prior has too much weight, it's way pulled over here. One thing to notice is that all these weights over here on the prior, they're not zero. And if they were zero, I would never be able to likelihood out of it. So if I zeroed out this range right here, multiplying likelihood into zero is still zero. So you can never get away from a zero prior, and you're never going to put mass there. So what would happen is this would budge up against that line wherever I put that threshold. If I ended up putting a zero block right in here, over the truth, it would smash up against that line is what would end up happening. It would actually look pretty fun. Not in a humorous way, just in a particular way. Let's look at some of these other ones. So more sensible priors. Oh, and let's just see what happens. If P was 1, and I ended up putting in some strong beliefs on P being half. So in some way, some people were thinking, hey, that's unbiased to do that. But of course, it's very biased to do this. This goes up. So that's kind of cool. So some people might say that's an unbiased belief, but that's like a mental trick. You're going to have to check to see what you mean. So when I ask people, what's the probability? A lot of times people do have priors that look like this. And they are really stacked right around 0.5, because I have a lot of people say to me, I don't know, 50-50. It's like, that's not an answer. You know, I need a number that's not 50-50. And what you really have, I can't distinguish those two things. I think it is the same. Okay. So you're starting to get that point right there. Let's look at a half and a half. This one looks kind of weird. We will derive this later. We're not doing it today. It's not a hard derivation. I need to tell you where the formula comes from. So I'm trying to make that make sense to you. So that's kind of cool. Look at that. You know, I left it that P was 1. So I only added a little bit of mass over here, but it's able to pull through this very easily. One thing I noticed about this prior is U-shaped. So it's going up there. So that's awesome. So it's lifting up some mass over here. The idea is that it's stacking mass around this right here and right here. If P was very, very small, if you didn't think something was going to happen, what we'd be seeing is very few successes. And so they would only happen once in a while. And what that's trying to do, it's actually mathematically derived, so I'm explaining it conceptually. So it's not trying to do something, it does things, but I'll speak subjectively and say it's kind of trying to just say, shield yourself from saying that P is 0. Don't say that. So say that it's possible that P is 0, or it's possible that P is 1. If you are never seeing something, or if you're seeing something all the time, it's exactly the same problem. So here would be the idea. So if somebody asked me, and if you've heard this metaphor before, bear with me for a second. If you wanted to measure the number of fish in the sea, and I created some experiment. I came up with a bucket, and I tried to go to the C. This is in a design class, so bear with me and say that I sample in an unbiased way from the sea and I get a bucket of water. I don't know what that means. And I come out with that bucket of water and I count the number of fish in there and I go, there's 0 fish in my bucket. So, and I know the whole volume of the sea. So I take the ratio of the volume of the bucket to the sea and I multiply 0 by that number, it's still 0. It's a horrible estimate of what P is. So I would say, I think P is 0. And then you would say, what's your uncertainty about it? And you might come up with a sort of walled interval, and you'd say P hat times 1 minus P hat divided by N, whatever N means. It has to do with the area, the volume of the bucket, but that's still 0. So you'd say 0 with variance 0. And it's a terrible answer. So maximum likelihood estimators can get you into trouble when you're estimating against the boundary. You can get really bad asymptotic results. The Bayesian has a different solution, and they say, put a little bit of mass over there, but don't cut too much. So, and that's what's very different from the beta half-half and the beta like 10-10, is the beta 10-10 is concentrating mass over here, where the beta half-half is keeping it real diffuse and shielding against these boundary effects. So some of these really cool priors do need things around boundaries. They shouldn't be uniform around them. Let me show you one more reason why the beta half-half can be a nice prior. I'm going to show you this picture. I'm going to have you simulate this soon enough. This is not a Bayesian analysis. Like, this is a non-Bayesian analysis. But this is what you might have learned in your Stat 101S type class. So to compute a confidence interval, probably what you did is you computed P hat to be equal to X bar. So and I'll call this the clumsy interval. I'll say they didn't lie to you in your Stat 101 class, but they definitely didn't tell you the truth. So, and then your interval is going to look like this. So I'll say the standard error is equal to the square root of P hat, 1 minus P hat, divided by N. So this is like sigma, what you compute. And in a Stat 101 class or any sort of stat class, I'd be shocked if you didn't see this before. So your confidence interval is going to be this thing. P hat plus or minus 2. If you don't like that, 1.96 is the closer number. So times BSE. This is a typical sort of wall approximation. And it's using the normal approximation. And they might have told you sums are normally distributed. Asymptotically, that's true if it has a finite variance. So that's true. And eventually the distribution they'll do inference off is the normal thing. So your Stat 101 type class, your high school stat class, I would say, has you do things like this. So I could play a game, and I could end up simulating from real P, just flipping points, just like I do in my current simulation study. And so for any P that I pick, let's pick this one, like close to a 0.5, right in here. I could sample a heck of a lot of times. I don't remember which N I picked from this, but I'm going to guess this is 30. So N is equal to 30. For 30 data points, I can compute this. So I sum up my 30 data points, I divide by 30, and then I'm able to compute this thing using that formula. So I can just take that P hat and plug it right in here. Multiply by 1.96, and I come up with a left or right hand down. And I can see if that interval actually covers true P. So I compute some interval, and I see if that covered true P. And I can check the rate of that by doing it over and over and over again. So that's what a confidence interval is. If that eludes you right now, go study up and read about confidence intervals, and I'll give you a real lecture on it eventually. So I'll try to compare Bayesian intervals to that. But this is just an idea, and I'm going to have you simulate this so If you aren't fresh on the idea, you will be after you do it. But that's what a confidence interval is actually trying to measure when they say something like 95% confident. So my coverage rate, if I use 1.96, should have uniform performance across P. When P is around 0.5, my simulated confidence intervals, the actual coverage rate, how often it covers the true P, is this blue jaggedy line. That's not working. 0.95 is this number, that's the knowledge line. So it always seems to be kind of underestimating it. It's not that bad. We could figure out what that's all about right here. This is not simulation error, why it's jigging and jagging. So you might think that's Monte Carlo error, so I can see your variability. If I cranked up n, it would look sawtooth like this. Does anybody know what that is? I'll ask you this question again later. It's not going to be on an upcoming quiz. We'll just talk about it when you actually simulate it. And be thinking about that. When P is very small, this interval falls apart. So when P is really close to 0, I never actually computed this for 0 because that would be stupid. Just 1 second. When I computed this for a number close to 0, this is 0.001 right here. And I did this whole thing, and I ended up simulating this over and over and over again. My true coverage rate is really close to 0, yet somebody would say it's 95%. Doesn't work very well at all. So that's the part where in your Stat 101 class, if you had P's that were near the middle point, I would say anywhere in here, 0.8 to 0.2, that analysis kind of works. But if you were doing actual science these days, everybody knows about the things that happen, regularly. The 0.5s, you sometimes see it, you sometimes don't. What people are asking questions about usually are the small probability events, like what's the probability of you having this gene or you getting a disease given this other fact. And you hope these things are small. If they were big, we wouldn't be here to talk about it. Your question?
Is it the same sawtooth pattern for all values of n, or is it?
It's not the same for all n. So I'll have you do this for different n. If you crank up n, this starts to raise. And it will get closer to that line. I have you do it for 1,000. I ask a question on this that I say, how big would n need to be if you were within 0.01 of the boundary? How big would n have to be for this blue line to be within 0.01 of the black line, so that the nominal rate was the same as what your actual rate was? So we believe it's 95. We know it's an approximation, but that your approximation is within 1%. What do you think? This is 30, so maybe I fumbled, and 31 would have saved the day. Probably, right? No. Chris?
I'm curious about what the sawtooth, what makes it in that shape.
I'm not asking that right now. So what's this number supposed to be? Keep thinking about that other thing, but just tuck it in your back pocket and think about it later. Go read about it, because somebody will explain it to you too.
I was just gonna say super big.
Super big. Why was super big?
A million.
No, it's not that big. So, yeah, it's like 10K. So it's crazy. So N31, I don't think so, even in this analysis. The beta half prior, if I did the exact same thing, this is N is equal to 30, looks like that. So I left the blue line up for scale. And the beta half prior gives me intervals. So I need to tell you what my interval means, but I built my posterior and I chopped 2.5% of the tail, and I chopped 2.5% of the tail, and I take that. That's actually what I did in here. So I take the, not even an optimal interval. So I came up with the symmetric interval. Turns out that posterior is highly unsymmetric. So what you should do is take the highest density part. So I did it because I could code it out in like 30 seconds versus the other thing would have taken me a little longer. So I did kind of the cheat thing just to show you, even using some approximations on the beta thing and doing the easy thing gives me much better agreement between the nominal rate, what I might be saying, and the true rate. So what I'm telling you is that by using the beta half-half prior, I'm a better frequentist than the frequentist. So maybe we started the class asking this question about what is a Bayesian? And some of us may have walked in and said the non-frequentist. And we've heard that a lot. Like, let's just stop with that because we need to define what we even mean. A confidence interval and the way that I was measuring the utility of that interval was perfectly frequentist. I used it in the confidence set. So the Bayesian interval was a much better confidence interval than this thing. Now, any one of my colleagues that are non-Bayesians would go, why didn't you use the Fisher's exact interval? And I thought, okay, that would, yeah. The beta is still a little bit better. So it's optimal, and that's what Jerry Brown showed. But I would say that would have been a lot better. But this really exemplifies, this is an asymptotic frequentist result, and a Bayesian result that is perfectly conditional on the data. I'm not using a frequentist result. I'm not saying that the distribution is normally distributed eventually. I'm using the beta to do everything. And it works much better. So that's one reason we like the beta half-half. Let's just look at it one more time, do another simulation. Lights, please. Massive set of lights. And then we'll jump over to the normal distribution. So beta half-half, that looks pretty good. And I'm going to make this point something more sensible, 0.72, and we'll just see how this might work. So let's do like 0.92, like a good science number. I like 0.92s. Seems like even when I'm talking about odds ratios and things like that, I tell people it's 0.8, and they're like, oh, what does that mean? And I'm like, you should do that thing. So they're like, I thought I needed to be above 0.95, and I'm like, you're mincing that with something totally different. So people around 0.92 is just whatever the number is, they're just freaking out. So it's just like any other number. 0.95s are no more special. So we can see that that posterior and the likelihood are tight. They're right on top of each other very quickly right there. And so the prior was able to walk, the posterior was able to walk away from that prior, but the prior still helps us on the boundary, as we could see in that coverage result. So there's different questions we could ask. How well do we estimate this? How good is our interval? So on and so forth. So how fast does the posterior pull away from the likelihood? And sometimes we can have optimal criterions simultaneously, and sometimes we can't. Let's talk about one such parameter where everybody always agrees. I wish I knew all this stuff when I was going to college. Then I could fix those stat 101 classes that I took. Still bother me today, but I'm going to count on you guys to do it eventually and go back and say, this is kind of true, but I wouldn't actually do this. So if I'm going to teach one thing in stat 101 classes and stay consistent about it, it would be the likelihood function. Over and over and over again, just getting people to think about likelihoods. Computing actual values, that's later. Let's jump to normal. So I'll say xi's are coming from a normal distribution. I'm going to say for this analysis, we know this. We will change that later. That will be our next analysis, is we'll learn what sigma squared or some function of sigma squared is. We're going to try to learn that. Infer. So we're going to infer from this stuff the data. And we're going to get to see n data points, everything is IID, even though I didn't write it. So I'm going to write down my likelihood function. I'm sick of dealing with the vector of data already, and I'm just going to jump to my other form of likelihood. So I wrote this down last time. This is proportional to e to the minus 1/2 x bar minus mu squared divided by sigma squared. I'll remind us that x bar is sum of the xi's divided by n. So just the arithmetic mean.
Seems a bit of an.
Oh, yeah.
I'm ready.
Yeah, yes. Thank you. I need to carry staff PhD students with me at all times. So, thank you very much. I wrote it down like this real quickly. So I could have written it down like this. We probably would get rid of that real quickly. Sigma e to the minus 1/2 xi minus mu squared over sigma squared. So this would have worked. If I didn't know anything and I wasn't familiar with the function and you just gave me the sampling density for each one of the xi's, I'd build it up this way. I wouldn't take a shortcut. This is a function of mu is exactly what this is a function of mu. They're exactly the same things. I would have written it like this if I wanted to just make myself feel more comfortable that that's the thing I'm staring at and that's where my eyes usually go. So I like to write it down like that. It doesn't make any difference. If I were doing a likelihood evaluation and if I were treating sigma squared as a parameter in the model and I wasn't locking it down, this function is not proportional to that function. But since sigma squared is locked down and it's just a number, and I don't care about it, it's some constant, I get to know it, this function is proportional to that function in terms of mu. So they're proportional to each other, they mean the same thing, they've got the same shapes. I would rather use this one. So, and then I have this question of which prior and why, and we've already kind of talked about this, that it's a normal, we just haven't really talked about what those two things are. So let's just walk through this and verify that the conjugate prior is normal, and once you've seen it once, what else can it be? So let's walk through that. I should like Velcro this to myself. Okay, so our posterior distribution, I could write cap x, I could write x bar. The data only comes through x bar. I could have written down some of the xi's in the other one and said the data only comes through some of the xi's, so that's how I'm going to think about the data being useful. Again, if I were trying to learn sigma squared, x bar is not enough to tell you what sigma squared is. You need the sum of the xi squared as well. So this is going to be proportional to my likelihood function, x, sigma squared. I could write this as x bar. I could write it as x. I can compute x bar from this, and that's all I need to know. So I'm using inconsistent notation, and it doesn't bother me. So I can either know all the x's, or I can know x bar, and to me it's the same. So then I'm going to multiply by my prior, and I'm going to be more specific, and I'm going to tell you that I've got some hyperparameters. This lecture is all about which prior and why, so we want to be specific about that. You won't always get people telling you what these are, and you should ask about them. If you have any question or concern, which prior and why? Always a good question. So if they get nervous and don't want to answer too much, it's either because you asked them why a flat prior on mu, or they have something to hide. So you either ask them too basic a question or one that they really don't want to answer. And the second one is one you want to investigate further. So I'm just going to write that down. I could write down the normalizing constant down here, but it's just a function of x. I'm going to integrate over mu. It's just some number, so I'm happy with this. So I'm just going to write this down, e to the minus 1/2 mu minus x bar squared, sigma squared over n. And then I've got some other prior right here, and it's some other normal distribution. And if you don't know why it's normal, it's because it's conjugate. It's going to make the posterior normal. And we'll see that in a second. So this is going to be a function of mu, expectation, squared divided by b. I could write over here 1/root pi and take the square root of the b and put it inside of there, but this is just a number. So again, these are given. So these are plug-in numbers. So I can write down an algebraic formula, but to have an actual posterior distribution, I gotta have data. This answer, this test statistic that I use for measuring mu is x bar, is the right thing to do. And then I need numbers right here to lock everything down, and now I can do an actual inference. So this is where the expectation is, and that's where the variance is. So the variance of the normal that we were building up was this, and now I'm thinking of that as the mean, so I've kind of interchanged their roles. So I had a sampling distribution over x bar that I turned into its likelihood function. When I observe the data, I can compute this. This thing right here is e to the minus 1/2. And I'm just going to expand some squares. This is mu squared minus 2 mu x bar plus x bar squared. Plus, and this is all over sigma squared over n. And this one is mu squared minus 2 mu e plus e squared, all divided by v. So I want to point something out. This is a quadratic function in mu. Again, the argument that we're looking for is mu, so that's our random variable. Everything else is locked down. So this is a constant, 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 and that's a constant. This is a function over all these mu's right here. So not the constants. This is a quadratic form. Adding a quadratic form to a quadratic form is a quadratic form. E to the minus quadratic form is always some sort of a normal. And that's all there is to it. So you can never have another distribution that's something different from a normal if it's e to the minus quadratic form. That's always a normal distribution. There's no other distribution in the world that looks like that. So what I need to figure out is which normal distribution it is. So when I have it written down like this, I'm probably not going to be able to do it in 2 minutes. I want to teach you how to do it, in fact, in less than that. So, and show you what the answer is. One such way to do this is to write this out as a quadratic form in terms of mu, complete the square, and write it down in a perfect square like these are written down. Factorize all the stuff that you use to complete the square outside of it. And it takes a little bit of time to do that calculation. I'm going to ask you to do it completely backwards. So instead of looking at a normal distribution like this, I'm going to go back to expanded form and get you to recognize which normal this is by identifying what the quadratic term is and the minus 2 linear term. It's a minus, for sure, minus there. And so we're going to come back and we're going to do something called what I call expanding the square, that allows you to not have to complete the square every single time you touch a normal distribution. So I'm going to teach you to do it backwards and faster. So, and if you want to complete the square, we will do that when we do posterior prediction on this problem. We'll have to do it. So, but I'm going to try to shortcut my way out of it. This is some normal distribution is what we have, and what we need to do is identify what the mean is and what the variance is. Then we have to ask ourselves some questions about it. What do they mean? So this original question of how do I pick those hyperparameters and why? So we're going to try to interpret them like we did in the Bernoulli exercise. And then I'm going to tell you what the reference prior is, the Jeffreys prior in one dimension. And then we're going to proceed with variance and do exactly the same thing. So we keep touching likelihoods, and we keep thinking about priors and how did we identify the conjugate prior, which parameters and why. So that's where we're at in the class. I do want to leave this up here. We'll do a review session tomorrow. It'll be at 6 p.m. It'll be in this room. Probability 0.2 that we'll need to switch the room. So if we do, that'll be easy to do. Probability 1 will find a room in this building. So if you had any problems with this, definitely come to review. If you didn't know what that meant, so if you're not sure how to compute that, if you have any questions about computing an expectation. So I saw several answers that are very close, and they're very close numerically, but the way you computed it isn't right. And so I can identify what that number means. So if you're wondering if you did do it right, if you normalize the likelihood times prior calculation and you averaged over that, and you use that weighted average, you did it correctly. So if you did just a straight uniform average where you divided by 8, because there are 8 numbers in there, you did it incorrectly. So it's just something to be aware of. Okay, if you know all about likelihoods, if you've taken an inference class in grad school before or something like that, we're still probably in this part of the course. We're about to start going. Thanks, you guys.